is the 29th lecture, and the topic for today is transistor characteristics and biasing. We have already seen the transistor characteristics under the common base connection. We had also briefly discussed the common emitter connection, which we would like to expand on today. In the common emitter connection, it is the emitter terminal which is common between the input and the output. Obviously, we are considering an NPN transistor. NPN transistor, and the currents are I sub E, I sub C and I sub B. Settle down quickly and quietly. These are the actual directions of currents: the base, collector and the emitter. Alright, the base emitter junction is forward biased and the collector base junction is reverse biased, and therefore the basic relation, one of the basic relations is that the emitter current is the sum of the collector current and the base current. And we also know that the collector current is a fraction of the emitter current, alpha IE, where alpha is less than 1, and in addition, because the collector junction is reverse biased, there is a reverse saturation current ICBO flowing in this circuit. Now, if I combine these two relations, these relations hold good under any connection of the transistor. What we are interested in is in showing how I sub C, the output current, varies as a function of the input current I sub B, because this is a common emitter connection. So what we do is we substitute for I sub E here from the first relation, and therefore I get alpha I sub C plus I sub B plus ICBO, and then take this term to the left hand side, this term, the term containing I sub C, and then I get I sub C 1 minus alpha in the left hand side should be equal to alpha IB plus ICBO. Alright, I am interested in finding I sub C as a function of I sub B, and if I divide both sides by 1 minus alpha, then the relationship that I get is I sub C equals to alpha by 1 minus alpha I sub B plus 1 by 1 minus alpha I sub CBO, the reverse saturation current. Now, we defined last time this quantity alpha by 1 minus alpha as beta. Then 1 by 1 minus alpha can be easily shown to be equal to beta plus 1, and therefore I sub C is equal to beta I sub B plus beta plus 1 I sub CBO. Alright. If you ignore this term, if you ignore the ICBO term, that is the reverse saturation current term, then you see that the collector current is exactly proportional to the base current, and the proportionality constant is beta. This is why beta is called the current amplification factor under the common emitter connection. Beta can be much larger than unity. For example, if alpha is equal to 0.99, then beta is how much? 99. Beta is 99. Beta can be much larger than unity. The other thing is that in the reverse saturation condition, in the common base connection, the relationship was simply IC equal to alpha IE plus ICBO. In the common base connection, the relation between input and output was simply IC equal to alpha IE plus ICBO, and ICBO formed a small fraction of the total current. Here you see ICBO is multiplied by a large quantity, beta plus 1, and if beta is 99, then this is 100 times ICBO, and therefore the reverse saturation current contributes to a much larger fraction of the total collector current under the common emitter connection, and this current is sometimes denoted by ICEO, that is, it is the equivalent reverse saturation current under the common emitter connection, alright, under the common emitter connection, and therefore my characteristics now become I sub C, the output current is beta I sub B plus I sub CEO, which is beta plus 1 times ICBO. Now let's look at this relationship. You notice that if the input current is 0, that is base is open, base does not contribute anything, then I sub C will consist of a small component ICEO, and this is independent of VCE, that is the collector to emitter voltage. It does not contain anything concerned with VCE, and therefore it is independent of VCE. In other words, if I plot the characteristics, and then beta equal to 0 will give rise to a characteristic like this, where this current is I sub CEO, that is, this corresponds to IB equal to 0. Now when IB increases to a non-zero value, naturally the collector current increases by the amount beta IB. So equal increments of IB shall cause equal increments of I sub C. Is that clear? Because ICU is a constant, alright, and therefore as we go ahead we shall have curves like this, each of them representing a certain value of IB, and IB is increasing in this direction. Suppose IB is equal to, let's say, 0.1 milliampere. For a particular curve there is a certain value of IB, alright, and suppose this curve when extended on the left meets this at, let's say, 10 milliampere. Suppose, can you say approximately what beta is? Approximately. If you ignore ICEO, then obviously the collector current, this is I sub C and this is V sub CE. It would be 10 milliampere divided by 0.1 milliampere, so it would be approximately 100. Now let's see some actual characteristics. Do not try to read what is written here, because I am going to spell it out. These are the common emitter characteristics of an NPN transistor, and this curve shows the input characteristic, that is IB as a function of VBE. As you know, in the common emitter connection, the base to emitter junction is forward biased. It is a diode, and therefore no wonder this characteristic is that of a diode characteristic. The base emitter junction, and you can see that it is approximately a straight line, which when extended to the x-axis, to the VBE axis, it will cut at a voltage of about 0.7. This is 0.5, 0.6, 0.7, and this is why we take the input junction, the base emitter junction, as equivalent to an ideal diode in series with 0.7 volt if it is silicon, alright. Now the output characteristic, that is the collector current I sub C versus VCE, as I said, when IB is 0, no base current, all you have is ICEO, alright. When IB increases to, let's say, 0.1 milliampere, well, the curve goes like this, and you see it cuts, if you extend this, it cuts at about 5 milliampere, and therefore this is a transistor with a beta of 50, 5 by 0.1. Similarly, when the base current goes to 0.2 milliampere, well, it cuts the axis at about 10, which corroborates the fact that beta is approximately equal to 50. And equal increments of base current should cause equal increments of collector current, and this is approximately true in practice also. This is what the collector characteristics look like, and this is the input characteristic. And as I said, we approximate the DC operation of the common emitter transistor, DC operation, in which there is a current IB, there is a current IE, and there is a current I sub C. Well, the input junction, base emitter junction, is a forward bias diode, and if this is silicon, then we approximate this by means of an ideal diode in series with 0.7 volt DC voltage, and this leads us to the emitter. If you are fussy, if you wish to incorporate the slope of this line, then you should add a small resistance. You should add a small resistance here, which for the present we ignore. And as far as the output is concerned, well, the output is simply beta IB plus ICEO, which is beta plus 1 IBO, and this is independent of VCE. As you can see here also, it is independent of VCE. It is almost parallel to the VCE axis, except for this region. Where VCE is so small that the collector base junction can no longer be reverse biased. It becomes forward biased, and this region where the current increases with VCE is a very small region, and is called the saturation region. We shall come back to this later. As far as amplification is concerned, we are concerned with the part of the characteristic where equal increments of IB lead to equal increments of I sub C. This is the region which we are interested in for amplification. Now, this characteristic I sub C equal to beta IB plus ICO can be represented by simply two current generators. One of them, well, this current is IB, the input current is IB, and this current is I sub C, this current is I sub E, and the two current generators, one would be beta IB and the other would be ICEO. This is the simple DC model of the common emitter transistor, and in any circuit analysis, well, you can utilize this equivalent model. Then life becomes very simple. Utilizing this model, one can now analyze to see why a transistor behaves like it does. Why does it amplify? Well, you see, here is a transistor, a common emitter transistor, which is connected to a positive supply here, VCC. It has to be connected to a positive supply because the collector base junction has to be reverse biased. This is an NPN transistor, this is N, this is P, and this is N. So N must be connected to positive supply to make it reverse biased. Then it is connected to the collector through a resistance which is called the load resistance, RL. This is the transistor. For simplicity, E is shown connected directly to the output, to the common terminal, and to the base are connected two sources, two current sources. One is a DC current source, capital I sub capital B, a DC current source, and this is an AC current source or a signal source, small IB. And therefore, the total current I sub capital B, total current, shall be the sum of the two, that is I sub capital B plus small I sub small b. Small I sub small b, this is a varying current, this is the signal current, whereas this is a steady current I sub b established by some battery. and some resistances, as you will see later. Now, if you look at the characteristics, we have plotted the same characteristics again. In addition, this red line here simply specifies the fact that VCE, the collector to emitter voltage, must be the supply minus the drop in RL. That means VCE is equal to VCC minus I sub C times RL, which is the equation to a straight line. All right. These characteristics are nonlinear characteristics, and therefore what we do is we have to satisfy VCE and I sub C should satisfy this relation and also the characteristic curves, and therefore we draw this straight line on the characteristic curves. How do you draw it? You put I sub C equal to 0, I sub C equal to 0, then VCE is equal to VCC. That means the straight line starts from this point, where this point is VCC, and then we put VCE equal to 0. Under that condition, I sub C should be VCC by RL, so it must pass through this point, which is VCC by RL, and you know a straight line can be specified by 2 points, so you join them and that becomes your load line. It is a straight line dictated by the load. It is a straight line dictated by the load, also of course the supply voltage VCC. All right. Now, to find out where the transistor operates, that is, what would be the value of VCC and I sub C, it must satisfy two equations. One is a nonlinear equation specified by the characteristic curves. The other is a linear equation specified by this line, and therefore the intersection of these two shall determine the point, the operating point of the transistor, or the so-called Q point of the transistor. And if I specify, if I figure out from here, from the characteristic curves, which one is the curve for the specified value of IB. Now ignore small ib. Small ib is a small variation or perturbation over the steady value of IB. I identified that this is the curve on which corresponds to the given value of IB. Then I find out where does it intersect. This is the point, and this is my Q point. Or left to itself, if there is no signal current, the transistor will sit at this point. Sit at this point means its VCE would be equal to this, and the collector current would be equal to this. This is about I don't know, 7.5. This is about 8, and this is about 4 milliampere. So 8 volt and 4 milliampere, that's where the transistor will sit. Now suppose on this base current, on this steady base current, is superimposed a small AC base current, small I sub small b, which for simplicity let us assume that it is sinusoidal with a peak value of 0.05 milliampere. That is, this point Q corresponds to 0.1 milliampere, and when the base current is maximum it becomes 0.15 milliampere. So the Q point shifts to this point because this curve is for 0.15 milliampere and this curve is for 0.05 milliampere. Equal changes in IB leads to equal changes in IC. This is the part that we are interested in. So when the base current fluctuates like this, when it goes through one complete cycle, what happens to the collector current? At the peak of the base current, the collector current reaches the value 6 milliampere. At the trough or the minimum of the base current, which corresponds to 0.05, the collector current is 2 milliampere, and therefore as the base current varies varies from 0.1 to 0.15, comes back to 0.1, goes back to 0.05, and then again comes back to 0.1. One cycle of the base current is completed. The collector current goes through a very similar variation. When the base current increases, collector current increases. And if these lines are equispaced, that is equal base current increments lead to equal collector current increments, then obviously this curve shall also be sinusoidal. All right. So a small base current here is able to control a large collector current here. If the peak to peak current here is 0.05 milliampere and the peak, I'm sorry, not peak to peak is how much? 0.1, and peak to peak here is from 2 to 6, 4. Okay. So when the base current goes through a peak to peak variation of 0.1 milliampere, the collector current goes through a peak to peak variation of 4 milliampere, and therefore the current amplification factor is 40. All right. A small current at the base can produce a large current variation in the collector. So there is current amplification by the transistor. In addition, if you look at the phases, when the base current increases, the collector current also increases. So they are in phase. All right. On the other hand, if you look at this voltage from collector to emitter, VCE, when the collector current increases, VCE decreases, and therefore the VCE variation shall be out of phase with the input current variation. Is that clear? It is also shown here that when the base current increases, the collector to emitter voltage decreases. All right. When the base current decreases, the collector to emitter voltage increases. So there is a variation, corresponding variation in VCE, but in opposite phase. And you see the voltage variation now goes from 5 to 15. That is, there is a 10 volt peak to peak variation. All right. And this 10 volt peak to peak variation is a large amplitude variation caused by a very small current variation at the base, and therefore there shall be a voltage amplification also. We would be able to say how much voltage amplification if we knew the equivalent resistance between base and emitter. Well, we shall calculate this later, but qualitatively, is the picture clear to you that the common emitter transistor can amplify current as well as voltage? This amplification, the faithfulness of this amplification depends on where your Q point is. That is, in absence of the signal, where does the transistor reside? For example, if your Q point is here, that is, the quiescent collector current is 0, then the transistor will conduct only when I sub B, small I sub B, is positive. Isn't that right? In other words, the transistor will now behave like a rectifier. That is, it will only produce the positive halves. All right. The transistor is sometimes operated under this condition, and this condition is known as class B operation, class B. All right. If the transistor is biased here, if the Q point is here, then obviously the positive halves, there shall be problems in amplification. The negative halves shall have less problem in amplification. In other words, the output waveform that you shall get shall no longer remain sinusoidal. It shall be distorted. All right. And therefore, for faithful amplification, where the base current variation shall lead to an exact replica, but an amplified or magnified replica in the collector current, you require that part of the characteristic where the lines are equispaced, that is, equal increments of base current lead to equal increments of collector current. This is the basic idea of amplification, how a transistor can be used as an amplifier. Before we take up this topic again in an actual circuit and see how the Q point is determined, let's clarify a couple of concepts, couple of terminologies that are used in connection with an amplifier. Amplifiers can be single stage or multi-stage. that is, if you use one transistor and around it you introduce resistors, power supply to get some amplification, one stage, that is one device, then it's called a single stage amplifier. Now a single stage amplifier obviously shall have limitation on the gain. How much amplification? How much amplification? So if you want more amplification or more gain, you might use two such stages. Such amplifiers are called multi-stage amplifiers, and it should be clear in the context whether an amplifier, a given amplifier is a single stage or a multi-stage. For example, a stereo amplifier is usually a three-stage amplifier. It is a multi-stage amplifier. The first stage is a voltage amplifier matching microphone to the amplifier system. Second stage is another voltage amplifier, and the last stage is a power amplifier, because you have to feed power to a loudspeaker. Amplifiers can be single stage or multi-stage depending on the frequency range of operation. Amplifiers can be classified as audio amplifiers, that is amplifiers which are useful in the audio range of frequencies, which is 16 Hz to 16 kilohertz. 16 Hz to 16 kilohertz. You can have, for example, VLF amplifiers, very low frequency amplifiers, like those used in biomedical applications, where frequencies encountered are of the order of a fraction of a hertz, or in process control, a sulfuric acid plant, where the variations are very slow, very low frequency amplifiers. Or you can have, let us say, video amplifiers, where the frequency range may vary from 30 Hz to about 4 megahertz or higher, okay, video amplifier, and so on. So you can classify amplifiers on the basis of number of stages, on the basis of the frequency range, then on the basis of the bandwidth. You might require an amplifier as you do in the case of a radio receiver or a TV receiver, so that only a narrow band of frequencies are required around the center frequency. Well, then it's called, such an amplifier is called a tuned amplifier. On the other hand, you can have tuned amplifier has a narrow band, okay, tuned or narrow band. On the other hand, if you want an audio amplifier, well, obviously what you need is something like this, where the 3 dB frequencies are 16 Hz and 16 kilohertz, and therefore this is a wide band amplifier. Okay, these are some of the terminologies that we shall be using in future: single stage, multi-stage, audio, video, VLF, and narrow band or wide band amplifiers. How do you characterize amplifiers? Now we consider an amplifier as a black box. There are input terminals, there are output terminals, and mostly amplifiers are characterized by sinusoidal inputs, and therefore one can work in terms of phasors. Let's say that the input phasor is Vi and the output phasor is Vo. All right, then the gain or amplification of the amplifier is denoted by V0, the ratio of the output phasor to the input phasor. Obviously, this would be a complex quantity. This would be a complex quantity. There would be a magnitude, which is the ratio of the two magnitudes of the voltages, and there would be a phase e to the power j theta. All right. If the gain, if the amplification is dependent on the size of the signal, all right, then obviously equal increments of the input current may not lead to equal increments of the output current. If that happens, then you have good amplification. But suppose you have an amplifier suppose you have an amplifier whose characteristic, ideal characteristic would be like this. Okay, the gain versus signal strength, let's say VI. No, I'm sorry. V0 versus Vi, it should be a straight line, all right, with a slope of magnitude of A, all right. Now suppose the characteristic is like this. Instead of a straight line, suppose the characteristic is like this. Then obviously a sinusoidal signal shall not give you a sinusoidal output. Is that clear? The output shall be distorted. Agreed? Such distortion is called amplitude distortion. Amplitude distortion. Is that clear? The characteristic that I want is that the output voltage should be linearly proportional to the input voltage. If this is not so, then a sinusoidal signal shall not give rise to a sinusoidal. It shall give rise to a distorted sinusoid, and under this condition we say the amplifier produces amplitude distortion, which is very commonly the case with public address systems, particularly those used for large rallies and so on. The voice is not detectable. In fact, if you put music on such a public address system, it is massacre. For musical reproduction, we require a very, very good linearity of amplification. On the other hand, speech, most of it is not paid attention to, so somebody speaks, that's about it. And there is a large crowd, okay? I'll make TV news. The actual content of the speech is not important, and therefore a lot of amplitude distortion is tolerated in a public address system. It cannot be tolerated in music. On the other hand, if you have an amplifier whose gain is sensitive to frequency, as I had said, for an audio stage it is like this, okay? Now suppose the 3 dB points are 30 Hertz to, let's say, 3.3 kilohertz, as is used in reproduction of speech signals. Then obviously if it is the full band audio, then such an amplifier cannot take, this is frequency in hertz, such an amplifier cannot reproduce the full audio, that is beyond 3.3 up to about 16 kilohertz. The gain has come down. Obviously this is also going to produce distortion. All right, this is like decreasing the treble. In a stereo set you have two controls, one is a bass control, the other is a treble control. Bass control means you either increase or decrease the low frequency 3 dB point. If you increase the bass, the drums will come better, the tabla sound for example. On the other hand, if you increase the treble, this means that you are increasing the high frequency 3 dB point. That means you are admitting more high frequency, and therefore a violin will sound sweeter if the treble control is increased. All right. The point that I am making is that if the signal consists of a certain band of frequencies and the amplifier cannot accommodate the total band, it accommodates only a part of it, obviously there shall be distortion. All right. For example, if you cut off the high frequency, Lata Mangeshkar will not sound like Lata Mangeshkar. She will sound like, I don't know, give a baser voice, Usha Uttup, would that be all right? Okay, so this distortion is called frequency distortion. We have discussed two kinds of distortion. One is amplitude distortion and the other is frequency distortion. There is still a third kind of distortion that one has to bother about, and this is the so-called phase distortion. I shall simply state this without proof, that phase distortion has to do with the angle theta. Theta usually is a function of omega. if theta is a function of omega, then no phase distortion shall occur. No phase distortion shall occur if theta is a linear function of omega, if theta is proportional to omega. All right, if theta is proportional to omega, no phase distortion shall occur. Now, let me mention to you a particular situation where the situations where phase distortion is important. Phase distortion, fortunately or unfortunately, cannot be detected by the ear. That is, our hearing capability is insensitive to phase distortion. Even if the phase is non-linear, it doesn't matter. But phase distortion, our vision is very sensitive to phase distortion. So in a TV, for example, the picture cannot have a phase distortion. If it does have a phase distortion, you will see all kinds of distortion. You will not see the correct picture. On the other hand, if it is the audio, the sound, we don't care what the phase distortion is. All right. Besides this general rule, you need not know much more about phase distortion at this point of time. Then what are the considerations in amplifier design? Considerations in amplifier design. As I had shown you with the help of the common emitter characteristics, obviously the Q point of the transistor is important. If the Q point is at a wrong point, then you might get lot of distortion in the amplification, and therefore the transistor must be biased properly. That is, your choice of VCC and the resistors used to bias the transistor to a particular VCE and a particular I sub C. These are the 2 points that determine the Q point of the transistor. You remember there was a load line and the Q point was somewhere in the middle. To establish this Q point at an appropriate point in the characteristic is an extremely important task. So the first consideration in amplifier design is its biasing. Then there are other considerations, like if you want a multi-stage amplifier, if you want to couple one stage to the other, well, then coupling is important. How do you couple? For example, you have one amplifier stage and another amplifier stage here. How do you couple? Suppose you connect the collector of one stage directly to the base of the next stage. Can you connect it directly? Well, the problem is that this would be at a high voltage, VCE. If you connect this to the base, then the base does not require that high voltage, and therefore DC coupling may introduce distortion. And what you have to do is to introduce a C here, a capacitor, so that DC is blocked but AC is passed. And there is a load here, RL. There is a load here. For every transistor there is a load, and therefore this coupling is called RC coupling, resistance capacitance coupling. All right. On the other hand, there can be other kinds of coupling. For example, if the capacitor is not there, then we call it direct coupling. It is not that direct coupling is not used, it is also used in some places. So direct coupling can be used, RC coupling can be used. One can also use transformer coupling, as is done, for example, at the last stage of a stereo amplifier. At the last stage of a stereo amplifier, the transistor feeds a transformer, primary, the secondary of which is connected to the loudspeaker. Okay, this is called transformer coupling. So coupling is an important consideration in amplifier design. Then the load, nature of the load. Obviously the load can be resistive, can be inductive, can be capacitive, all kinds of loads. For example, a loudspeaker is usually considered as a resistive load. On the other hand, a radio frequency stage may have a load like this. You may have a load like a parallel tuned circuit, parallel resonance circuit. What is the impedance at resonance? Infinity. What is the impedance at resonance of this circuit? Infinity. And therefore, you will see later that the gain of such an amplifier is proportional to the load, and therefore you expect infinite gain from this. Actually, you don't get infinite gain because the inductance has a resistance, the capacitor has a resistance in parallel, and therefore you can get a large gain. Alright, and that's how you get a characteristic like this, a tuned characteristic. So the nature of the load, whether it is resistive, inductive, capacitive or tuned, is important. It is also important to consider when you are connecting one amplifier stage to another. Suppose this is stage 1 and this is stage 2. It is important to consider what is the input impedance of this stage, Z in, and what is the output impedance of this stage, ZO1 and Z in 2. It is important to consider the relative proportion of these two. Alright, suppose ZO1 is very large and Z in 2 is very small. Alright, then only a small fraction of the first stage output shall be coupled to the second. Isn't that right? Because the Thevenin equivalent says that you have ZO1, a voltage source, then you are connecting to Z in 2. If Z in 2 is very small compared to ZO1, then obviously very little voltage shall go to the second stage. So what is the consideration then? ZO1 must be very small compared to the input impedance of the stage that it couples to, Z in 2. Alright, this consideration is extremely important. On the other hand, there are situations where when you are not interested in transferring voltage, you are interested in transferring power. Well, what do you do there? You make impedance matching. That is, if you are interested in transferring maximum power from this stage to this, then ZO1 and Z in 2 should be complex conjugates of each other, and therefore it is important what your application is. You have a transistor, you have a load, alright, and you have a plus VCC. You have a load RL, you wish to establish a particular VCE and a particular I sub C. So the condition will be satisfied if you can find out the appropriate base current and establish the corresponding base current. And one of the ways that this can be done with a single battery is that the same battery is connected to the base through a resistance, let's say RB. Alright, then this will be the base current, the DC base current I sub B. Okay, this is the circuit. This is one of the simplest circuits for establishing, for biasing a transistor. Obviously, I sub B, the base current here, shall be equal to the drop in RB. What is the drop in RB? This is VCC minus the drop between base and emitter. And if you recall the DC equivalent circuit, it is 0.7, and therefore this will be VCC minus VBE, which is 0.7 divided by R sub B. Alright, and the job seems to have been done. This will be IB, beta times IB plus ICEO shall be I sub C. I sub C will be beta times IB plus ICEO, which normally is negligible, and therefore if you know the beta of the transistor, you know what is I sub C. Alright, and if you know I sub C, then you can determine RL to find out a specific value of VCE. For example, if VCE is required to be 5 volt and I sub C is required to be 1 milliampere, with a beta of 50, then you know what your IB required is. IB will be 1 milliampere divided by 50, 0.02 milliampere. And if VCC is 12 volt, then 12 minus 0.7 divided by the resistance, that will determine IB. So you know RB, all right. And then since you know collector current 1 milliampere, you want 5 volt here, so 7 volts should be dropped here. They are very simple calculations, and therefore you know RL. The disadvantage of this is that if this transistor goes bad and you replace it by another transistor of the same type, then the Q point will go haywire. The reason is the following, that in mass production of transistors, even though they are produced by the same process, about a 1000 is perhaps the minimum number that is produced or fabricated in one go. These transistors vary very widely. In other words, beta can vary by a ratio of approximately 6:1. You can have a lot of transistors, 2N110, 1000 of them, and you go on measuring beta. The lowest beta may be as low as 30, the highest may be as low as 180. 6:1 variation, and therefore as soon as you replace the transistor, the Q point changes. Similarly, this, as you see, ICEO is beta plus 1 ICBO, and as soon as temperature changes, ICBO, as you know, doubles for every 10 degrees centigrade rise in temperature. The law of variation of ICBO approximately is that it doubles for every 10 degrees centigrade rise of temperature, and therefore if temperature changes, then ICBO rises, this quantity changes, and therefore once again the Q point goes bad. Not only that, the most drastic disadvantage of this circuit is, now you have to follow me carefully. Suppose due to a small change of temperature in this circuit, I sub C increases. Suppose due to a small change of temperature, I sub C increases. This collector current increases. Now what happens? If the collector current increases, naturally the heat dissipation in the transistor also increases. That is, VCE times IC increases. Alright. Now this heat is generated here and is to be dissipated in the transistor, and therefore it causes a further rise of temperature. Alright. If I sub C increases, temperature increases. If temperature increases, I sub C further increases. Alright. And this can now be a merry-go-round situation, and ultimately the transistor will be burned. This process is called a thermal runaway. This process of burning a transistor should never be resorted to, but it does happen in practice, and the process is known as thermal runaway. It should be avoided, and this is one of the main disadvantages of this particular circuit. A circuit in which this does not happen has to be designed on the basis of a different kind of philosophy. The philosophy in this circuit was to establish a particular IB, to establish a particular base current. The base current is a constant. The collector current is not a constant, alright, because it varies with beta, it varies with ICEO. If I change the philosophy of maintaining a constant I sub C, base current, let it adjust to get a particular value of I sub C, then this process of thermal runaway shall be arrested. And this is done by a circuit which is known as a self-bias circuit. It's a very simple circuit. You have two resistors here. This is plus VCC. This is I sub C. Call this R sub C and call this R sub E. In the emitter also there is a resistance, and the base is biased not through one resistance but through two resistances, that is R1 and R2. R1 and R2. If you look at this circuit from the left of this line, obviously it's a battery VCC supplying a series connection R2 and R1. The drop in R1 then supplies the base. The base voltage VBG ground, you call this simply VB, is simply the drop across R1, which is equal to VBE plus the drop across RE. Now let's see what happens. Suppose I sub C due to some reason increases. What is the current through this? What is the current through RE? IC plus IB. This is the current IB. Now see what happens qualitatively. We shall analyze this quantitatively later. If I sub C increases, then I sub C plus I sub B also increases. If that increases, then what does it happen? What happens? The drop across RE, you call this VE. VE increases. If VE increases, then what happens to VBE? Decreases. Isn't that right? VBE, this drop, shall then decrease. If VBE decreases, what happens? I sub B. If the diode voltage decreases, I sub B decreases. And I sub C is nothing but beta times I sub B plus ICEO. So if IB decreases, then what happens to IC? IC decreases. You see, the increasing tendency of IC is arrested. In other words, there is a feedback mechanism which tends to keep I sub C stable, and in such a connection the transistor can never burn down. Thermal runaway is arrested, and this is one of the most popular biasing circuits. Next time we shall make a thorough analysis of this and see the stability of the biasing.